reason, it's automatically rejected. It's not open for discussion. It's not open for going to court. It's not open to rerunning samples and so forth. Okay, so zero tolerance means they will not accept anything that tests positive. Now, that also means that the cost of food in Japan is much higher than in the United States or in Korea. But they are really fanatics about food quality. Okay, so I've already mentioned in Japan a little bit about pesticides and veterinary drug residues, and the key number to remember is 820 different MRLs for pesticides and veterinary drug residues. Also, oops. Also, there's a big study on shellfish in general, and a lot of new regulations concerning the toxicity of marine biotoxins. Now, marine biotoxins are almost always found in shellfish, shrimp, crayfish, any fish that's a bottom feeder, like catfish, for example. Now, marine biotoxins are quite challenging to analyze in an analytical laboratory. And I'm going to show you some examples in this afternoon of these methods. But what I wanted to convey to you is that up until now, one of the problems in testing for marine biotoxins has been that there weren't any standards. There weren't any primary standards that you could use for quantitation. Well, we saw this problem about 2-3 years ago and are now working with the NRL, which is the National Reference Laboratory in Canada. And the Canadian government, I think, is the first place in the world today where you can buy primary standards that are certified standards for marine biotoxins. That's a very, very challenging standard to test. So those are now becoming commercially available, and that was all done in collaboration with our food safety program. And we introduced a lot of new technology to that laboratory, and they taught us a lot about marine biotoxins. So it's a good example of two companies and two laboratories working together to solve a very challenging problem. All right, now melamine I won't stop to talk about because Guiping Liu is here today from Beijing, and she has a lot of firsthand experience with melamine. Melamine was not her fault, but she's been very instrumental in working with laboratory methods to detect and screen and quantify melamine. All right, now if I go next to China, China has a lot of other similar activities, and one of them is that now you've got a nation that's changing the rate of food exports. The rate of food exports are larger than any other country in the world. That means that the Chinese have a big, big challenge to test all of these foods and make sure that they meet the European standards, the Japanese standards, the Korean standards, and so forth. So testing is changing rapidly in China, and that's why Guiping is there as a food safety specialist to help them and support them with these challenging methods. And you'll hear her talk about productivity and laboratory throughput today. So, and again, we're very proud of the fact that we're collaborating with the Chinese to help them with these new technologies to improve that. As I said earlier today, the melamine came out, the methods for melamine came out of China and the United States and Europe. All of those were done on Thermo Fisher Scientific LCs and mass spectrometers. It's kind of interesting because when the Food and Drug Administration developed their method for melamine, they used the lowest cost liquid chromatograph that we sell. It's a very, very basic HPLC, and it's low price. And yet that was good enough to develop an LC MSMS method. So it says that these methods, we believe the methods have to be rugged and robust, that anybody in Korea could run those methods, or China, or United States, or any other country. The other thing that's important in China right now is the new food safety law. And that's really got a lot of pressure on looking at international exports of foods and vegetables, of course. And it also means that a lot of testing is being increased because of this new food safety law. It also is making some organization changes. It's also increasing the technology base in China. So it's kind of interesting because the United States is also within 90 days of passing a new food safety law for the same reasons. The United States is very far behind in food testing. So a couple of interesting things have happened in the United States, and one of them is that we have a new president of the United States, President Obama, and excuse me, and he is very passionate about improving food quality. He's very concerned about public health in the United States. Now, John Gilbert mentioned, for example, that in the UK, people in England like to eat strawberries 12 months of the year. Well, the way you do that is you have to import foods all over the world, and they're constantly being shipped around the world. The same thing is true in California, where I live. We eat grapes now 12 months of the year, and yet California can only produce grapes for about 4 months of the year because of the weather and climate and so forth. Well, so as a result, you've got to have standards in food testing laboratories. And up until President Obama came to the White House, we would ship grapes in from Chile in shipload quantities, and they are offloaded in the port of Los Angeles, right near Los Angeles, and they're put onto big trucks, and they go to all different parts of the United States. They go in the grocery stores, and my wife buys grapes every week, and we just go home and eat the grapes. No testing, no inspection. We just assume that they're good. Now, in Korea, I know that you test the grapes because you get your grapes from the same place we do, and so does Japan. And the Japanese are testing all these grapes, and they're finding lots of contamination. In the United States, we just eat the grapes, and we're just happy to keep eating the grapes. Okay, so there's something wrong. So President Obama is now funding a lot of money into food safety. Currently, they have openings, and they're trying to hire something like 1,400 PhD chemists in the Food and Drug Administration alone. It's really going to change the way food is tested in the United States. And of course, also, then the commissioner of the Food and Drug Administration, which in Korea you would call that a minister of Food and Drug, or the KFDA, and this would be the minister of Agriculture, and those are all new people. Well, they're all very pro-food, as you might imagine. Now, he has, besides the passion for food, he has another passion, and that's for spending money. And he is spending so much money that the United States has now got a balance of trade problems that we've never seen since the Great Depression. So the good news is the food gets better. The bad news is the economy got worse. Okay, all right. So let me show you a few examples of what I would suggest that you might want to look at. And I'll use the first example as pesticides from the European Union. Now, the EU uses all performance-based methods. They do not use prescriptive methods, so don't look for them. What they do with performance-based methods is they will set the norms and they'll set the standards for your method. And you have to, and I have to, demonstrate that our methods comply with the standards of performance. I'll show you that in just a minute. Now, some of those standards for performance include MRLs, for example, and you notice that some of these MRLs are really quite low at the 0.01 milligram per kilo level, or in other words, less than a part per billion. Okay, and the total number of MRLs that they have in the European Union is about 150,000 different MRLs, which cover about 500 different pesticides. Now contrast that with Japan. This number in Japan is 820,000. This number is the same in Japan, and their list of pesticides is about 1,000. So again, you see the Japanese taking a lot of initiative here. And it's not about who has the biggest list of MRLs. The question is how do we ensure quality of our food supply? So if you look at the website for the European Union, and you'll find several directives, and I pointed these out. They're in your notebooks. There's 3 of them that are important to you. One of these directives talks about the sampling method that you use to collect the sample, transport the sample, and preserve the sample. It is not about how to prepare the sample for analysis. It's not about sample preparation. That's up to you and to me. This is about how to do valid sampling to know that you get samples that are legally defensible and you minimize the number of false negatives. Okay? The second document describes performance criteria for these methods. Now, performance criteria usually require things like determining the LOQ, or the limit of quantitation, level 1, level 2 precision, sometimes single laboratory validation, linear dynamic range, so forth and so on. So they're the same kind of metrics that you would normally use for method validation anyway. So those criteria are spelled out for you in this directive right here, and that's well documented. Okay, and the third one that's helpful is look at the Senko directive based in 2007, which talks about method validation and how you go about validating multi-lab validation for methods, and the quality control that's required as part of the method validation. Now, if you've ever done multi-lab validations, you know that this is a challenging exercise when you're working with laboratories other than your own, trying to get the same data quality. I'm a member of the board of directors on AOAC International, and we recently had a delegation from China come and show us that they had several hundred new methods that they wanted validated. Well, they thought that validation was just to put a stamp on the method. No, now we're helping them understand what it is to do multi-lab validation. And in fact, that's work in progress right now. They also have a senior scientist that's spending a year in Washington learning how to do method validation. So it's taken very seriously for quality of methods around the world. Okay. Now, I thought what I would do is to show you an example of how we go about modifying methods, because that's what people like to do. They would like to get better results in a shorter period of time with less skilled people in the laboratory and less cost. Well, for pesticides, for example, there is a relatively new method for sample preparation, and it's called the Catcher's method. And the Q stands for quick, E stands for easy, C stands for cheap, E stands for effective, R is rugged, and S is safe. Okay? In other words, this is a pretty universal sample preparation method. It's being widely adopted in the United States, Canada, and in Japan and Europe, and I heard a couple people talking about it here in Korea. It's a method that is a good universal method for sample preparation, and it's much easier and much more effective than older sample preparation methods, which require multiple steps of liquid extraction and 3 or 4 different steps of solid phase extraction, for example. So we took this method and said, I wondered if we could simplify the method even further if we use the specificity of a GC triple quad mass spectrometer. In other words, using MS-MS spectrometry, because the advantage is that you get very high specificity, and if you get very high specificity, you should get high sensitivity. Okay, so instead of doing so much sample cleanup, what we did was to use and rely heavily on the MS-MS spectra for eliminating background and other interferences. So here's the method in a workflow diagram. We just start with 10 grams of sample, like John Gilbert described. You do an acetonitrile extraction and salting out with magnesium sulfate and sodium chloride. Then you homogenize the sample, centrifuge the sample. There's only one step in chemistry here, and that's using a graphite carbon solid phase extraction cartridge. Okay. Well, actually, liquid-liquid extraction is a chemistry step, and the SPE is a chemistry step. But that's all. The rest is simply reducing the sample to dryness, taking it back up into a solvent that's compatible with a GC column, like acetone and hexane, for example. Okay, and then run this on the GC with a triple quad mass spec. Now that's quite that's a much simpler method. It's a much faster method because the sample preparation time is significantly reduced. If you're interested in the details of that method, Guiping Liu will take you through the original method this afternoon, and also we have a publication that appeared in a journal called Separation Science, of which Guiping is a co-author in this article, and we'll be happy to get you copies of this. The reason I like this article is because it tells you every single detail, every possible detail to use the Ketcher's method. So I recommend that to you, and the way you should get a copy of that is through the Euroscience office here in Seoul. All right, now just to show you the results here, I'm skipping some slides, but to show you some results, if you use MSMS spectrometry, then you always utilize what we call a selected reaction monitoring. Now, if that's the molecular ion or the parent ion right there, and some of these are SRMs, in other words, the selected reaction monitoring products or daughter ions. But there's also a lot of interferences in here because in this particular case, we didn't do a very good job of sample preparation or sample cleanup. So that's why there's a lot of peaks in here, and there's also some chemical noise in there. Because if you have matrix effects, you'll get chemical noise mixed in with your spectra. Now, if you go to something that we call what we call highly selective SRM, now that's will be described also in detail later today. But right now, I just wanted to show you that capability removes all of these daughter ions, and it removes all of the noise and the background and interferences. And now look at that parathion peak. You notice the baseline is perfectly clean, which means you've got now a very, very selective detector for parathion. So in fact, it allows you to look at a daughter ion, in this case, without any interferences, and you've decreased the sample preparation time by at least a factor of 3, if not a factor of 5. So the spectra become quite a bit simpler, and of course the quantitation that you get with that peak compared to that spectra is significantly different.